We talked about obtaining or computing the powers of a number under some modulus value earlier, but especially when the modulus value is prime, we have a more efficient way to compute the powers. And this is through Fermat's little theorem. And let's see the statement of the theorem first. If p is a prime number and a is an integer such that p does not divide a, so it's the number a is not a multiple of the modulus value, then a to the power p minus 1 is congruent to 1 modulo p. Actually, if you remember, we had done the proof of this earlier in class. This was one of the earlier exam questions, so I had solved this. But let's remember the proof. And this proof actually is one of the many proofs of Fermat's little theorem, and this is due to Euler. And this is based on induction on the number A. So first of all, we write the statement as, rather than a to power p minus 1 congruent to 1, we write this as a to power p is congruent to a modulo p. And for the basis step, you can also use 0, because 0 to the power p minus 1 is congruent to 0 modulo p, or rather 0 to power p is congruent to 0 in any case. You can also use a equals 1. Either case works. In the inductive step, remember this is induction on a, not, not p, because the derivation works for every prime number p. The inductive hypothesis is for some k value greater than or equal to 1, k to power p is congruent to k modulo p. And of course here k should not be a multiple of p. And by the binomial theorem, consider the following: k plus 1 to the power p. And by the binomial theorem, we can expand this as this statement here. The sum from I equals 0 up to p choose I times k to power I. So this is simply, you can write this as p choose 0 k to power 0 plus p choose 1 k to 1 plus p choose 2 k to 2 p choose 3 k to 3 plus dot 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 up to, let me put it here, p choose p minus 1 k to power p minus 1 plus p choose p k to p. Okay, so this is the general statement of this expression. And here you see I have written this as a sum of 3 terms here. One of them is 1, and that corresponds to actually this term here. The other is k to power p, which corresponds to this term here. And the rest are these other terms. So what is the significance of the other terms? The significance of the other terms is that they are all divisible by p, because if you look at the expressions, it's in the form of p choose I, where I is not 0 and not p, so it's between from 1 up to p minus 1, and any of those expressions, p choose I, is going to have a factor of p in it. Okay, so for instance, p choose I, in the general case, it's going to be I factorial, p minus I factorial, p factorial divided by I factorial, p minus I factorial. And the primality of p is essential here, because we are going to have the factor of p in this factorial, and also it's not going to be cancelled out by any of the numbers in the denominator. So for instance, if p is not a prime number, let's say 4 choose 2, for instance, that is 4, 3 divided by 2, and 6. So you see, this is not divisible by 4. But that is not the case here. When p is prime, it's not going to be canceled out or simplified by any value in the denominator, as you can do here, something like this. So that's not going to happen when p is prime. Therefore, all these terms in between, these ones, are divisible by p, which means under modulo p, I can get rid of them. So if I take modulo p of both sides, what I get is k plus 1 to power p modulo p is congruent to k to power p, this term, plus 1, this term, modulo p, because all the others are divisible by p. Okay, and the final step, k to the power p modulo p, based on our inductive hypothesis, is congruent to k. Therefore, if you plug that in, you get k plus 1 to the power p modulo p is congruent to k plus 1 modulo p, which completes the proof. So this is the proof of Fermat's Little theorem, and as I said, it has many other proofs, which we are not going to go into. This is quite a famous theorem, and many proofs have been laid out. But we are going to see the applications of this. First, let's see an example regarding exponentiation here. Let's compute 7 to power 222 modulo 11. And earlier, we attacked such problems as, first of all, writing the powers of 7, where the power value is, or the exponent is, a power of 2. And we tried to find either a pattern, or we just, let's say, partitioned the exponent value 222 into powers of 2, and then multiplied all those values to obtain the result. Here we follow a different direction. First of all, we recognize that the modulus value 11 is prime. Therefore, Fermat's Little theorem is applicable here. Therefore, well, then another issue is that 11 is not a factor of 7. Therefore, we can write that 7 to power 11 minus 1 is congruent to 1 modulo 11. And therefore, I can write 7 to power 222 as 7 to the power 220 plus 2. And this is going to be 7 to power 220 is going to be written as 7 to power 10 to the power 22. But this here inside is just 1 congruent to 1 modulo 11. Therefore, we can just get rid of this. And therefore, this is simply congruent to 49 modulo 11, which is 5.